Hello, Brian Miller-Hicks here, my series on earth science and geology, and we're going to tackle oceans. Huge subject, of course, and oceans deserve their own science, the science of oceanography. Um, the history of this planet is indelibly intertwined with the origin and the presence of our oceans. We would not be here without the oceans. The oceans are the birthplace, so to speak, of many forms of life. It's thought that early life evolved as early bacteria and algae in the oceans, and then later evolved and migrated to land. The water in the oceans, the origin of the oceans is quite old, dating back to perhaps 3.8 billion years ago, so fairly early in the history of our planet. The origin of the water in the oceans is thought to have come from the interior of the Earth primarily, and with contributions by comets from outer space. So it's a very complex, very large ranging subject. Affects us, the presence of our oceans today affects us in many ways, from the creation of storms over the oceans that affect our weather and climate, of course, to providing a source for our food, to providing us recreation, of course, and a means of transport. So oceans are a big subject, very important to us. Let's get going. This is a volcano, of course, that is actively erupting, emitting ash, rock fragments, and steam. The important thing to note here is that steam, of course, being water vapor, is emitting gases and water vapor into the atmosphere. It's thought that early Earth, of course, was molten, then it cooled enough to form fragments of rock, and early volcanoes would emit huge volumes of gases, carbon dioxide, water vapor, and so forth, into the atmosphere. The water vapor, especially when Earth's atmosphere was cool enough, would condense into clouds, and the rains began, and the rains continued for thousands, perhaps millions of years, filling up the low basins in these primitive rock fragments of the early continents to form our primordial oceans at that time, some 3.8 billion years ago. Now, as I already mentioned, most many oceanographers believe that most of the water on Earth came from the interior of the Earth. Magma contains all the elements that we know that are present on the Earth, including water. But comets may have delivered some amount of water to our oceans, which is kind of an interesting, exciting thing to think about. Earth's first oceans were quite primitive. The atmosphere as well was not breathable early on. There wasn't a lot of free oxygen. It was mainly nitrogen, carbon dioxide, other gaseous compounds that were not amenable to oxygen-breathing organisms like us. So 4 billion years ago, the oceans also were different than they are today. They were very rich in iron. They're possibly green in color instead of blue. These funny little structures you see here in the foreground are organisms, or the structures that organisms built that we call stromatolites. We still have organisms that are similar to these bacteria and algae-like organisms back that very long time ago, that build layers of calcium carbonate around themselves, and they build up these structures that are like primitive reefs, so to speak, and what you see here in their layered forms. So again, stromatolites were ancient primitive organisms. They did not need or use oxygen. The oceans themselves were rich in, or the atmosphere itself, excuse me, was rich in methane, hydrogen, nitrogen, and carbon dioxide. Okay, so it's quite a different picture that long ago. The evolution of the oceans and the evolution of the atmosphere sort of worked together. Finally, after long periods of time, there was enough organisms in the ocean that would use nutrients and convert seawater, convert elements into free oxygen. So that created enough free oxygen to start filling the ocean with oxygen, which gradually escaped from the oceans and went up into the atmosphere. So the release of free oxygen by organisms many billions of years ago is responsible for building up enough oxygen in the atmosphere that we now, as evolved oxygen-breathing and nitrogen-breathing organisms, can use. So let's look at the structure of the ocean. That has to do with the geologic structure of the ocean basins. Oceans are held within giant depressions, if you will, basins that are scattered through over the entire planet. The map of the Earth's oceans shows that we have the Atlantic Ocean, of course, between the east coast of North and South America and the west coast of Africa and Europe. We have the Pacific Ocean, which of course is the largest ocean on Earth. We also have the Indian Ocean, the Southern Ocean, and the Arctic Ocean. All these oceans are filled with water contained in ocean basins, which, as you know from our study of the tectonics, has not always been the way you see them here on this map. Ocean basins open and close relative to the activities of plate tectonics through many hundreds of millions of years. So early on, or a couple of hundred years ago, we really didn't know a lot about the oceans. It took many voyages of discovery and this particular ship was the HMS Challenger from England from 1872 to 1876 to explore the ocean. These red arrows and lines are the pathways that this particular ship took during that time. Early journeys or voyages were meant to discover as much as possible about our oceans, to measure the depth of the ocean basins, to gather, collect specimens of organisms, to check the composition of seawater and so forth. So it took a long time for us to learn about our oceans through these many explorations. Early on, methods of determining ocean depths would be fairly primitive. You get a weight, attach it to a very long rope or cable, and lower that into the water. Often these cables were not long enough to reach ocean bottom, and they often gave deceiving depth measurements because ocean currents would drag some of these lines out and give you a false reading on your depths. So it really wasn't until around the 1940s, World War II, that we developed enough sophisticated instrumentation to get accurate ocean depth measurements. That's the depth of water from ocean surface down to ocean floor. And this shows echo sounding and sonar, where you take a sound signal, emit it from a ship, bounce it back off the ocean floor, and the time it took to get from the ship to the floor and back to the ship Since we knew the speed of sound in water, we could figure out the depth of the ocean at that particular location. First, we used single beam sonar, echo sounding. Then we started to use multi-beam, which could sweep a larger area, and even supplemented that with something called a towfish, which emitted its own set of signals. So we started to use these techniques and technology to achieve more accurate mapping of the ocean floor. As you know, as we discussed during tectonics, these measurements of the ocean floor were critical, extremely important in taking our thinking from continental drift to plate tectonics in terms of realizing that plate tectonics is heavily dependent on what happens at seafloor ridges or rises where plates are splitting apart, and what's happening on the ocean floor where plates are diving back into the interior of the Earth at ocean trenches through the process of subduction. So figuring out what happens on the ocean floor through these plate movements was vital in figuring out plate tectonics in the long run and piecing things together. Another technique for getting ocean floor depths is using satellite data. Same principle, more or less. Shoot radar pulses to the sea surface and back to the satellite to get a measurement of the ocean surface, which mimics more or less the shape of the sea floor. Okay, let's look at water, seawater. What is seawater made of? Well, of course, primary ingredient is water. So if you take a liter of seawater, most of it, 965 grams, is water, H2O. About 3% or so is salt. Okay, that salt is composed of different elements. Sodium chloride, of course. Sodium chloride makes what we know of as salt, table salt. But there's also other ions, sulfates, magnesium, calcium, potassium, strontium, bromine, and carbon. So everything, all these elements are dissolved in seawater. And as I said, seawater salinity on average is around 3–3.5%. That can vary according to where you are in the oceans and whether you have any dilution by fresh water. Salinity changes due to these effects. Salinity can increase where we have evaporation of seawater. Why is that? Well, when seawater evaporates through being evaporated by the sun, heat of the sun, the water that rises from the sea surface is water vapor, doesn't take the salt with it. Okay, the water vapor is fresh water. Salt stays behind, so that the surface layers of seawater become more salty because of that evaporation. When you freeze seawater, same effect. Frozen seawater, ice, seawater ice doesn't have the salt in it, so that you have freshwater ice with a very saline, salty layer underneath. Salinity will decrease by dilution when you get mixing of freshwater from rain and snow mixing into seawater to dilute the salinity, decrease the salinity. Melting of ice, so the opposite effect of freezing would be melting, which releases that freshwater ice back into the ocean. And of course, a contribution from runoff from rivers, and also groundwater flow into the ocean. All that is fresh water, which tends to decrease the salinity. Let's look at two major factors of that we're interested in measuring in terms of seawater properties: water temperature and water density. The temperature of seawater, of course, it varies according to where you are. You might guess, and you'd be right, that the temperature of seawater in the tropics, in the Gulf of Mexico, would be warmer than surface water temperatures near the Arctic or near Antarctica or the polar regions. Density is affected by temperature. Warm water is less dense than cold water. Cold water is higher density. Density, of course, is the property of a substance that has to do with weight per unit volume. A material that's more dense has a higher weight per unit volume. So salty, cold water has a higher weight per unit volume of water, therefore it's more dense. That means that cold, salty water will tend to sink, and warm, fresher water will tend to float. Okay, that's important to know. That means that the ocean has a layered structure. This is a very simplified graphic showing that the ocean has a surface mixed zone, which is being roiled by currents, by waves, by wind, and also by the exchange of gases. It tends to be oxygen rich and tends to have temperatures dependent on where it is on the Earth's surface, whether it's tropical or polar, and so forth. Then we have a transition zone, which is a little cooler, so it's a little denser, and the deep zone, which has the coldest water down near the ocean floor, coldest water, the densest water, so it sits down near the ocean floor, the bottom of the ocean. Let's take a closer look at the ocean floor and what coats the ocean floor, if you will. What drapes over the entire ocean floor all over the world is sediment. Sediment, of course, being particles of sand, silt, and clay, as well as trillions of dead organisms that die and settle to the bottom of the ocean, plus the other stuff like shipwrecks, pottery, chandeliers, what have you, that collect and settle down to the bottom. Okay. So here's the Atlantic Ocean. This is the mid-ocean ridge. Look at this line, which is the cross section, point A to point B, going across the map, point A to point B, going across this cross section. So if we look at this cross section, we see the shape or the configuration of the Atlantic seafloor basin, the Atlantic Basin. Going from left to right, here's North America. Here's what we call the continental shelf, which is a pretty flat extension of the continent, now underwater. In times past, during times of glaciation, maximum glaciation, for example, much of this continental shelf was exposed because sea levels were much lower because so much water was locked up in ice. Okay, so we continue our journey down across the ocean basin, and we're descending this part, which is called the continental slope, and getting into the deep ocean basin. Then the seafloor rises as it goes towards the mid-ocean ridge, which can be many kilometers across in width and pretty high, 1,000 feet or so at the peak of the mid-ocean ridge. And then you descend the mid-ocean ridge slope going towards the east into the deep ocean basin and back to the continental margin again. So it's a general configuration, the general shape of a seafloor of the Atlantic Ocean basin. Now, all through here, especially this part and this part, there's sediment continually settling onto the seafloor, contributed by rivers coming off the continents, contributed by sediment that's blown by the wind, contributed by many trillions of organisms that live and die in the ocean and settle to the bottom. So all these parts of the ocean floor are draped with sediments, as I say, which gives us an interesting look at the history of deposition on these ocean floors. Another process that that contributes sediment to the ocean floor is the occasional turbidity current, which is a phenomenon that happens when sediment-rich currents dip into these deep, steep submarine canyons and run out to the sea floor as fans of sediment. So this is sort of analogous to a river on land carrying silt, sand, and clay in its channel, and then coming out to a lake or a desert basin or the ocean floor and dumping that sediment out because it's being slowed down, it's dumping its sediment out. Okay, this happens many times over, and what you get in terms of a stratigraphic or sedimentary section is something like this, which is called graded bedding. Graded bedding means you have coarse material where the current first slows down and dumps its coarse load, and then more gradually it'll dump its finer sediment so that you have coarse sediment on the bottom, fine sediment on top, and then through repeated episodes of turbidity current, you get a stacked series of graded beds that look like this. Okay, this is one current, second current, a third current. And the piles of sediment that are built up by these turbidity current onto the seafloor are called deep sea fans. Let's take a look at how seafloor sediments are distributed globally. This is a very useful graphic that shows two major classifications of sediment you'll find on the seafloor. First is called terrigenous, from the Latin word terra, which means land or earth. And the second is biogenous, which has to do with biology, so organisms. Terrigenous sediments are primarily mineral matter, sand, silt, and clay. Out here around the continental margins, you see this white band here, around Africa here, around Australia, and so forth. Around all the land masses, that's the coarser material that's dumped out by rivers. So sand, silt, gravel. The currents don't have enough energy to carry these coarser sediments out real far into the ocean basins, but they do have enough energy to transport the real fine stuff, the fine clays, which end up farther out into the basins as these salmon-colored areas. See here, 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 out here. These are fine sediments carried farther out into the ocean basins by currents, by waves, by wind. Okay. The biogenous sediments occur throughout the Earth's ocean's seafloor, and that's the purple, calcareous, and the yellow, siliceous. Okay, calcareous is the remnants of organisms that use the elements of seawater, calcium, carbon dioxide, to manufacture calcium carbonate to build their shells. So any organism that builds a shell made out of calcium carbonate contributes calcareous sediment as they live and die and settle to the seafloor. It's called ooze because it mixes with clay on the bottom and becomes this jelly-like oozy substance. Siliceous means these are the remains of organisms that build not calcareous shells, not calcium carbonate shells, but shells made of silica. They take silica from the seawater to build their little homes around themselves, live and die, settle to the seafloor, and mix with the seafloor muds to become siliceous ooze. This is a photograph showing some of the types of organisms that make up these seafloor sediments. Radiolaria, here, for example, are organisms that use siliceous shells, shells made of silica. Foraminifera have shells made of calcium carbonate. What are these scientists doing? They're looking at deep sea sediment cores. These gray tubes are actually one, let me explain this. Scientists want to learn more about the composition of the seafloor and the composition of the sediments that make up the seafloor. So they go out with ships that have equipment that take steel tubes, basically, and run them down to the seafloor. These are hollow steel tubes that are driven by drilling mechanisms that penetrate the seafloor sediments and encase these sediments into these hollow steel tubes. They bring up these steel tubes when they're full of sediment and take them out and bring them onto the deck of the ship. And then take these steel tubes, cut them in half, and examine the cores of the sediment that are contained within these tubes. There's a wealth of information they can gather from looking at these sediments. They can look at the composition of the muds, the silts, the clays, the texture of the soil of the sediment. They can look for the remains of organisms within these cores to determine what kind of life lived so many years ago. Keep in mind, the deeper you go with these cores, the older the sediment is that you're looking at. So one example of data they can get from the organisms is certain organisms will give you information on the seawater temperature or the composition of seawater in terms of oxygen content and so forth. So these sediment cores are very, very useful in obtaining, as I said, a wealth of information of life that lived at the time these sediments were deposited, the sort of environment that these organisms lived in. Scientists can extract pollens from these cores to give us an idea of what sort of plant life was living along continental edges, and the pollen was blown into the sea, and that gives us more information as well. So a lot to be learned from these, and scientists are continually looking at these cores to understand more about what's going on in the seafloor and what's going on in sediments that are derived from continental land masses and that are derived from the actual sediments that are settling into the seafloor or onto the seafloor bottom.